So in this video we will briefly see what is quantum computation and quantum information, and I'll be uploading a series of videos in the future to explore the field of quantum computation and quantum information. The prerequisites to understand these topics is that you must have a fair understanding of linear algebra and quantum mechanics. You can check out my quantum mechanics playlist to understand Dirac notations and operators in quantum mechanics. Feel free to watch these videos at 1.5x or 2x as I'll be talking at a leisurely pace. So let's start with the video. What is quantum computation and quantum information? It is the study of information processing tasks that can be accomplished using quantum mechanical system. But why do we need them? Well, at the turn of the 20th century, a series of crises had arisen in physics, with the absurdities predicted by the classical theories on topics like ultraviolet catastrophe or electrons spiraling into the atomic nuclei, resulted in the creation of the modern theory of quantum mechanics. And ever since, it has been an indispensable part of science. Quantum mechanics is a mathematical framework or set of rules for the construction of physical theories. And as the name suggests, quantum computation and quantum information is one of the application of quantum mechanics, where we aim to obtain complete control over a single quantum systems with the hope of discovering new and unexpected phenomena. Now let's briefly talk about Moore's law, which was given by Gordon Moore. This law briefly states that computer power will double for constant cost roughly once every 2 years. This law has approximately held true in the decades since the 1960s. But in some times this dream run will end. With the computer technology running in difficulties in size, quantum effects are beginning to interfere in the functioning of electronic devices as they are made smaller and smaller. One of the solution to the problem is to move to a different computing paradigm, that is to quantum computation, which is based on the idea of using quantum mechanics to perform computations instead of classical physics. So without a further ado, let's start learning more about this field. So we know in classical computation, information is stored in classical bits. A classical bit can have two values, either a 0 or a 1. In quantum computation and quantum information, we have quantum bits or qubits for short. But how does a qubit different from a classical bit? A qubit is a mathematical object, although it can be realized as an actual physical system. But for our current purposes, we treat qubit as an abstract mathematical object. The difference between a bit and a qubit is that a qubit can be in a state other than 0 or 1. It can be defined as a linear combination of states or superposition of these states. That is, suppose for a state psi representing a qubit, it can be given as alpha 0 plus beta 1, where alpha and beta are complex number, but for our most purposes we will treat them as real numbers. This state of a qubit is a vector in a 2D complex vector space. The state 0 and 1 are known as computational basis state, and they also form an orthonormal basis for this vector space. When we measure a qubit, we get either a 0 or 1. The probability of getting a 0 is given by alpha square, and the probability of getting 1 is given by beta square. And naturally we have this condition that alpha square plus beta square will be equal to 1. The ability of a qubit to be in a superposition state runs counter to our common sense understanding of the physical world around us. On contrary to a classical bit, a qubit can exist in a continuum of states between 0 and 1 until it is observed. One useful geometric representation for thinking about qubit is given by the block sphere, which is a unit 3D sphere representing a single bit. And since alpha square plus beta square is equal to 1, we may write psi, which is equal to alpha times 0 plus beta times 1, as psi equal to cos theta by 2 0 plus e raised to I phi sine theta by 2 1, where theta and phi define a point on the sphere as you can see from this representation. But one restriction to this visual representation is that it is limited for a single qubit, and there is no generalization for multiple qubits. Another question arises about a qubit is how much information is represented by a qubit. Well, as I said earlier, measurement of a qubit will give only either 0 or 1, which is paradoxical as there are infinite number of points on this unit sphere. So in principle, one could store an entire book in infinite binary expansion of theta. Furthermore, measurement changes the state of a qubit and collapses it from its superposition to a specific state. That is, for a state vector representing a qubit, measurement of this state, if suppose, gives us 0, so the post measurement state of the qubit will be 0 state. One may ask the question why? Well, it is simply because of the fundamental postulates of quantum mechanics. So if you want to study this topic in more detail, I am referring to this book of Quantum Computation and Quantum Information by Nelson and Chong. You may refer to this in order to study this topic in much more detail. In the next video, we will study about quantum gates, how we represent multiple qubits and Bell state. We will define a theorem called as no cloning theorem, and we will also try to study quantum algorithms and much more. So stay tuned for that.